Let me show you how these calculations are done in practice. So in the folder number 7, I have created several examples for you. There is an example of spin polarized DFT calculations for cobalt to iron aluminum, LSDA+U calculations for nickel oxide, and also I took one rare earth system. For all these three materials, we will calculate exchange interactions now. And also I have included a program init_jijs, which will generate the input green.inp files for these calculations. Let us start with the first example. This is a converge calculation. We can have a look at the outlast file. Indeed, we have very low value of FSQ, and we have the following magnetic moments. As you remember, in this material we have two distinct types of magnetic atoms. One of them is cobalt, which in fact has two sides, and also we have one iron. There is also a tiny magnetic moment on aluminum, which will not be taken into account. So before we start, we have to generate the k-point mesh, which samples the entire Brillouin zone. To do this, we go to the directory called BZ, and we copy the file which contains the symmetry operations. It's called SymCof. Copy it right here, and we give it another name, such as LSDA+U. Okay, we open this file, and now what we have to do is to change the number of symmetry operations to 1. Because this way the code will not read any symmetry operations after the first one, which is identity. Good. Now we can run the program called cube for generating the k-mesh. And by default it takes the SymCof file from the directory above. In this case, we have to use the newly generated file called LSDA+U instead. Include time reversal? No. And now we enter the k-point dimensions. And this calculation was done with 16 times 16 k-points, and we had a shift of 1/2, 1/2, 1/2. Now we hit enter a couple of times, and you see that we got a new file with a new k-mesh. So let's compare it with the one which we used to have. So this is the old k-mesh file, and this is the new one. As you can see, the difference is only that in the first case we had 60 irreducible k-points, and in this case we have 2048, which coincides with the total number of k-points. And each k-point has a degeneracy 1. So that's exactly what we wanted. So now we can go up and link this newly produced k-mesh to the calculation. Now the postfix is 16_1, like so. Good. And now we have to create the green.inp files. So let me use the script which automatically generates them. It was located just one directory above. We just hit enter to execute it. It's a very simple code. What it does is actually going through the out file and checking for the values of the magnetic moments. And as soon as the value is larger than 0.5 Bohr magneton, the atom is assumed to be intrinsically magnetic, and therefore it will be used to calculate the JIJs. In our case, we have two magnetic types, iron and cobalt. Aluminum will be left aside because its magnetic moment is smaller than 0.5 Bohr magneton. We got 3 new green.inp files. Let's look at the first one. It uses the default number of Matsubara points, which assumes that we have a temperature of 400 Kelvin. The code also assumes that there is no self-energy to be read. You have to change these flags to false, true, false in the old format, or just true, false in the new format. This is the default projection for Brianna. And this is the block controlling the exchange interaction calculations. We use projection 1, which means that we use the same projection as Brianna. In this case, it's Muffington heads. This file was generated for the first magnetic atom, which was cobalt, and it has a global index 1. The code will now look for all its neighbors in the radius of 3 lattice constants. To speed up the calculation, let's reduce it to 1.5. And here are the indices of magnetic atoms in the unit cell. And finally, in the cluster block, we specify the states, which are used for calculating the exchange interactions. In this case, we only use d orbitals of transition metals. Cobalt-1 and cobalt-2 atoms belong to the same type, but they have two different side indices. We can have a look at the second file. Here we will calculate all the JIJs between cobalt-2 atoms and the rest. And let's again just modify this radius. And finally we go to iron. It's here. We also reduce the cluster. We will have to run 3 calculations for each of these green.inp files. And the simplest way to do it is to create a little script, which I already placed here. So let's have a look. It's called run jij. So the script will just loop over indices 1, 2, and 3. It copies the green.inp file to its proper name, because that's the only one which is used by RSPt. It will run the code and save the out file with a separate name. So let's give it a go. Good, looks like it's done. Let us look at the first produced out jij file. At some point it starts the jij calculation, and here are the main settings for this calculation. So it says that we use non-relativistic version and only isotropic exchange will be calculated. This is done automatically because we don't have spin-orbit coupling. Otherwise, in the case of relativistic calculation, it becomes a tensor and we have to calculate all components of it. We use the same projection as in Brianna, which in this case is muffin tin heads. And here it says that in total it generated 190 neighbors, but only 18 of them are inequivalent, because what the code does, it looks for the neighbors and then it applies symmetry operations from SymCov file and find only the ones which are symmetry inequivalent. This way we only compute the interactions with only one atom belonging to each coordination shell. And here are all the neighbors listed. This is the central atom, which is cobalt-1 in our case. And here is its nearest neighbor, which is of type 3, which means that it's iron. It's located at a distance 4.69 Bohr away from the central cobalt atom. And in fact, there are 4 neighbors of this kind. The calculation will be done only for one of them. Next line says that we have 6 next nearest neighbors, and they are of type 2, means that they are also cobalt atoms. And later we have indices of atoms written here. So these indices correspond to the elements of the observer cluster block, which was used for the jij calculation. We had the d states of 2 cobalt atoms and 1 iron atom. And here we can see that each atom is represented by 10 orbitals. It's d states, as expected. And here it prints the local exchange splitting, which is in fact just the local Hamiltonian up minus local Hamiltonian down. And in case of d orbitals, it becomes a 5 by 5 matrix. Here is a calculated value of the spin moment on the central atom, which is cobalt in our case. It's close to 1.2 Bohr magneton, and it's indeed similar to what we find in the out file of a self-consistent calculation. This value here is calculated using the Matsubara mesh specified in the green.inp file. And if this value is too different compared to the self-consistent value, it means that most likely you don't have enough Matsubara points in your calculation. And here is a table of calculated exchange parameters. The nearest neighbor coupling is 1.3 millirydberg. It's pretty big, but that's what we expect for a Hosler alloy. It has quite high Curie temperature. The next nearest neighbor coupling is already much smaller, and you can see that it decays with the distance. And finally, here is a reminder that positive J corresponds to the ferromagnetic coupling and negative J corresponds to antiferromagnetic one. And here, this is also quite important. In principle, what the code does, it calculates the second energy derivative with respect to the spin rotations. In order to get a value of a jij, we also have to know the magnetic reference state we are dealing with. What is done inside RSPt is that the code analyzes the exchange splitting, it takes its trace and checks whether it's positive or negative. So if the trace is negative, it means that the magnetic moment is pointing up, because it means that the spin-up states are lower in energy compared to the spin-down states. So here the code assumes the following directions of the magnetic moments. In my experience, it never fails, but you have to be careful. For example, if you have several orbitals on every atom. In our case, we have a ferromagnetic system where all the spins are pointing in the same direction and the code identified it correctly. So it means that we can trust the signs of the JIJs. If you see that this table is wrong, then you have to flip the sign of certain JIJs. But as I said, I never had to do it. What we can do now is to have a look at all three files at the same time. So the first two correspond to cobalt-1 and cobalt-2 atoms, and the third one calculates the exchange interaction of iron atom with all its neighbors. So it makes sense that it's a little different. So we go to the bottom and we can compare, for example, the exchange splitting. We can see that on iron we have much larger exchange splitting, and as a result also larger magnetic moment. These two quantities go hand in hand, so it makes perfect sense. So that's it for this first example, and now we can proceed to the second one. So here it is. This is LSDA+U calculation for nickel oxide. And again, as you can see, it's converged. And the magnetic moments on nickel atoms are about 1.7 Bohr magneton. Again, we check what was the k-point mesh used in this calculation. So it was 12 times 12 times 12. We go to the BZ directory, we copy the simconf file. Now we call this file low with only one symmetry operation, and we regenerate the k-mesh. (12 times 12 times 12), and we use the shift of 1/2, 1/2, 1/2. Okay, then we link it to the calculation. We use 432 k-points, which maybe is not big enough. On the other hand, for insulators, it's quite typical that we'd use less k-points. So if I needed to make sure that the calculation is converged, maybe I would do the calculation with few more k-point meshes. And every time I would converge the calculation and then run the JIJ. But for the moment, let's assume that it's okay. The difference with respect to the previous calculation is that here we in fact already have a green.inp file, which in our case controls the LSDA+U calculation. Let me run the script for generating the input files for the JIJ calculation. As you can see, we got two new files. So let's have a look at these files. Everything seems to be in place, but by default the script assumes that there is no self-energy. So this is something we have to correct for. Let me see what was specified in the green.inp file for the self-consistent calculation. We had just a spectrum block and these two clusters. And since we're gonna read the self-energy, this is the necessary information for it to be read properly. So I copy these lines, which define the impurities on nickel up and nickel down atoms, and I put them in here, anywhere in this input file. Because now the JIJ block will only use the observer cluster, so the cluster with index 0 where no U and J is specified. But it will also use these clusters to read the self-energy. But to read the self-energy, we have to modify these flags here. And in the new format, we have to specify here readsig and SCS flags. In our case, we have to read the self-energy, so this flag is true, but there is no charge of consistency because we will only run one calculation for the JIJs. We don't want to update the self-energy, so we set the second flag to false. For the DFT+U calculation, we needed only one Matsubara point because the self-energy was static. However, when you calculate the JIJs, you need a mesh of Matsubara frequencies because you're gonna take some integral of your Green's function and the exchange splitting. And it doesn't matter if the exchange splitting is static. The Green's function has energy dependence, and in order to integrate it properly, you need many Matsubara points. So this is it for nickel up, and we can prepare a similar file for nickel atom 2. All what we have to do is, in fact, to change this index here. And we are set to go. Again, we will calculate the JIJs using the projection used in Brianna, which is muffin tin heads in this case. I have prepared a similar script called run JIJ, which will now loop over these two magnetic atoms. Let's run it. Okay, it's done. And we immediately get the list of neighbors. It looks like we have 12 nearest neighbors in total. Some of them are of the opposite direction of magnetization, some of them are of the same, and we have also 6 next nearest neighbors. It looks like the code correctly identified all the indices of magnetic atoms. Now it also printed us the self-energy at the first Matsubara point. This is just a sanity check that the self-energy is read properly. And this is the self-energy at the last Matsubara point. And since we have a DFT+U calculation, they coincide because the self-energy is static, meaning that it's the same for any Matsubara frequency. So it's just additional contribution which will be added to the Hamiltonian, for example, before calculating the exchange splitting. So if you look at this exchange splitting, it's pretty large, and you can actually calculate this value by hand. If you go to the self-energy matrix and you take this element corresponding to the first D up state, then you go to this one and it will be the first D down orbital, and you take the difference between these two values and you add it to the difference in the local Hamiltonian, and you are supposed to get roughly minus 0.28 Rydberg. The spin moment is close to 1.73 Bohr magneton, and it's similar to what we had in the out file of the self-consistent calculation. And now we get the table of calculated JIJs. The nearest neighbor coupling is almost 0, and it is supposed to be so because the nearest neighbors have so-called 90-degree superexchange. So for this configuration, in fact, we are supposed to have tiny superexchange according to good enough Kanamori-Anderson rules. The next nearest neighbor coupling is on the opposite, corresponds to the 180-degree superexchange. We get it quite large and negative, meaning that it's antiferromagnetic. And this is also in agreement with good enough Kanamori-Anderson rules. And here the code assumed that the reference state is antiferromagnetic. And again, we can trust these signs. Okay, that's it for this example. I was thinking it's quite instructive to show you LSDA+U calculation because the self-energy is static, so we needed only one Matsubara point to calculate the self-energy, but the JIJs have to be integrated on a grid of Matsubara points. And finally, let's go to third example. This is HCP terbium. The calculation was converged with this K-mesh. So let me just generate the full mesh here. Let me link it. Now let's have a look at the out file of the last iteration. The calculation is indeed converged, and if we look at the magnetic moment, it's 6.56. But in fact, the calculation was done using 4F as core, so 6 Bohr magneton come from non-interacting core, and only 0.56 is formed by the valence electrons. But anyway, the script init_JIJs only analyzes these numbers, so I would suppose that it will generate us the good starting point for the JIJ calculation. So let's run it. It found one type of magnetic atoms, but in fact the structure is HCP, so there will be two atoms, and indeed we got two green.inp files. Let's look at the first one. We will calculate the neighbors of the first terbium atom. Let's reduce this cluster to 1.2, for example. In the unit cell we have two magnetic atoms where global indices are 1 and 2, and in the cluster block we can see that they are in fact equivalent. They belong to the same type. But by default the script init JIJs assumes that we have d transition metal with d orbitals taken into account. We have to add s and p states as well. So it means that in total we have 6 states and we're set to go. Okay, now we can copy this file and make a similar input file for the second terbium atom. All what we have to do is to change the index of the central atom here. Okay, the calculation is done. Let's have a look at the first out file. And you can see the calculated exchange integrals. You can see that the code assumed that both spins were pointing down and in the same direction. It's correct because, as you remember, in the self-consistent calculation we got minus 6.56 Bohr magneton per terbium. However, here the calculated spin moment is just minus 0.56 Bohr magneton. Why is it like that? Because it is calculated from the cluster block where we only had SPD states taken into account. The F states belong to the core, so they don't contribute. So it's correct because this is the value we would expect for these states. So that's it. We went through a couple of classical examples. We considered a metallic system, we considered an insulator, and also we took one rare earth system. Here is a list of some general recommendations, what I would suggest to use when you run the JIJ calculation. First of all, try to use multiple tails for the orbitals of your interest. For example, in transition metals it's 3D states, and for lanthanides it will be 6s, 6p, and 5d states. This way you will make your basis more flexible and also the results will be more robust. You, in principle, don't have to use the same projection what you use for the MFT part and for calculating the JIJs. The most important thing is that the self-energy file, when it's read, that it's properly projected. So you shouldn't modify the projection which is used by Brianna, but instead in the JIJ block you can use another projection. And it becomes quite useful, for example, if you work with transition metal alloy and you have some self-energy produced by DMFT using Muffington heads projection. You can read the self-energy in this basis, but when calculating the JIJs, you can use generalized OR, because generalized OR is known to give you more robust results, and I strongly recommend to use it for metallic systems. As a general suggestion, I also recommend to use negative tails. Well, first of all, it's more safe. It's less likely that you will get some convergence problems, but also I noticed that the JIJs are more robust. And here are some specific recommendations. For metallic systems, I recommend using generalized OR scheme. So this is JIJ projection 2. For transition metal oxides, it turns out that this projection gives a little too delocalized states, and instead Muffington heads projection provides results in the JIJs in much better agreement with experiment. And my explanation is such that if you have two delocalized states, then you don't get a proper description of a super exchange mechanism, and you start to get some kinetic exchange contribution which you are not supposed to. And finally, for rare earths, my experience suggests that you can safely put 4f electrons in core, but when you calculate the JIJs, make sure that you use all S, P, and D states in your cluster block. So that's it for today. See you next time, and until then, enjoy RSPt.